that explains the nature of reality. However, there are some people, like the famous science communicator Neil deGrasse Tyson, who think that this theory might be incorrect. Tyson even goes as far as to say that dark matter doesn't really exist. So what exactly is string theory? Why does Neil deGrasse Tyson have doubts about it and the existence of dark matter? And why does he believe in the idea of the multiverse? Let's find out.
You know, I was all for it back when they started that adventure back in early 80s, in 1982. And in fact, at the time I was at the University of Texas, where some of the leading thinkers at the time were based. And string theory is like the theory of everything. It would get you an understanding where Einstein's theories end and pick up it would allow you to divide by zero legally, okay? That's what string theory would allow you to do. It'll allow you to describe the universe at the moment of the Big Bang, which is where right now our theories can't get us there, possibly even before the Big Bang. It would unify the science of the large, general relativity, with the science of the small, quantum mechanics. All right, if that's the case, fine. I asked him, how close are you? He said, a couple of years away, we're almost there. So 1985 rolls by. Oh, how's it going? We're going well. How close? Oh, a couple of years away. They've been saying a couple of years for 27 years, 26 years. So I'm kind of losing enthusiasm. But they're the only game in town, and they're really cheap to fund. Let them do their thing. I don't have a problem with that, because they're the only game in town. I'm not going to stop them, but I'm losing my enthusiasm. And you ask them, they say, it's a very hard problem. Now, again, the book was titled Optical Illusions, Not Brain Failures. So a string theorist will not say, we are all just too stupid to figure this problem out. But maybe we as a species are too stupid to figure it out.
Our universe is made up of matter, but when we take a closer look, we find that this matter consists of incredibly small particles. These particles come in various types, like electrons, quarks, and neutrinos, among others. These tiny building blocks of the universe move around and interact by exchanging other particles. For example, the electromagnetic force responsible for interactions between charged particles is mediated through the exchange of photons. All of these diverse particles find their place in what's known as the Standard Model. This is our most accurate mathematical framework that helps us understand the quantum world. The Standard Model puts particles into two main categories: fermions, which form the basis of matter, and bosons, which are responsible for explaining how particles interact with each other. When we first take a look, it might seem like the Standard Model explains pretty much everything we need to know. But there's one big missing piece: how gravity works on a larger scale. We have general relativity to explain gravity, describing how massive objects warp space and time, attracting other objects toward them. Just like the other forces, we suspect that at the smallest level, the curvature of space-time is made up of incredibly tiny particles called gravitons. However, when we try to fit the concept of the graviton into the Standard Model, we encounter a problem. Our calculations produce strange and unrealistic results, involving values that shoot up to infinity, which we can't make sense of. This issue makes it incredibly difficult to understand how gravity works on the tiniest scales. As a result, physicists have been on a mission for more than 50 years to find new theories that can help us solve this problem. In this video, we're going to explore one of the most promising solutions: string theory. The main idea behind string theory is surprisingly simple. In the Standard Model, we think of particles as being like point-like entities with no dimension. But we believe this might not be the whole story. According to string theory, this point-like representation is just an approximation. If we zoom in even further, we might find that particles are actually made up of incredibly small strings. Think of them as tiny, stretchy rubber bands. These strings have a property called tension, and they're able to vibrate. You can imagine this like the strings of a guitar, where different vibrations create different musical notes. Similarly, these little strings can vibrate in different ways: one way, two ways, three ways, and so on. These various patterns of vibration correspond to different types of particles that we observe in our world. When we run the calculations, we realize something amazing. Some of these vibrating strings behave like particles that we're already familiar with, such as photons, the particles of light. And even more remarkably, some of these strings behave like gravitons, which are believed to be responsible for gravity. So, by starting with the idea that particles are these tiny vibrating strings with tension, we can actually explain why we have different kinds of particles and predict the existence of gravitons, which could help us understand how gravity works on the smallest scales. Now, we want to figure out how these strings move and change as they travel through space and time. To do that, we can use a similar approach to what we used in our current models. Imagine you're shooting an electron toward a target. The electron behaves like a wave, and when it hits the target, we can't be certain exactly where it will land. At the quantum level, this experiment can yield different outcomes each time. We can only predict the likelihood of different results happening, not the exact outcome. The goal of quantum physics is to calculate these probabilities. The way we calculate these probabilities is to consider all the different ways a particular outcome can occur. This involves considering all possible paths the electron could take and all the potential interactions it might have with other particles. For instance, an electron might emit a photon and then absorb it again, or it might emit 2 photons or even 3. By considering all these different scenarios, we can determine the probability of a particular outcome. In string theory, we follow a similar approach, but instead of particles being represented as points, they're now represented as strings that trace out surfaces as they move through time. To calculate how a string evolves over time in a probabilistic manner, we consider all the possible shapes and patterns that the string can form as it vibrates and moves. This includes considering how the string follows a particular path, how it vibrates, and even how it might split in two, effectively emitting a new particle or coming back together, absorbing a particle. By accounting for all these possibilities, we automatically include interactions between particles in the theory without needing to add them separately. Interestingly, interactions in the previous standard model occurred instantly, like the emission of a photon. However, in string theory, interactions are more gradual and continuous. Instead of particles being emitted and absorbed instantly, these interactions happen more smoothly over time. This characteristic helps address the issues we face when trying to incorporate gravitons into the standard model, as these gradual interactions help prevent the problematic infinite values from arising. This way, not only does string theory predict the existence of gravitons, but it also provides a framework to calculate how these gravitons interact with other particles. This is a significant advancement in our quest to understand quantum gravity. So far, this theory holds great promise. It not only offers an explanation for the variety of particle types, but also predicts their interactions and provides insight into the behavior of gravity on the smallest scales. However, as with any scientific endeavor, there are challenges that need to be overcome. One of the central challenges that string theory grapples with is the behavior of strings themselves and the absence of certain particles known as fermions. In traditional particle physics, particles are often depicted as dimensionless points, each with specific properties. String theory, however, posits that these particles are not points, but tiny strings akin to miniature rubber bands that have the ability to vibrate. These vibrations determine the various particles we observe in the universe, from photons to gravitons. Yet, this gives rise to a puzzling observation. All the strings in theory behave like particles known as bosons, which include photons and gravitons. This presents a perplexing question. Where are the fermions? Fermions are a distinct category of particles that include electrons, the building blocks of matter. They possess characteristics like mass, charge, and spin that set them apart from bosons. The existing version of string theory struggles to predict the existence of fermions within its framework. This discrepancy between the theory's behavior and observed reality presents a substantial hurdle that physicists are laboring to overcome. Another challenge that string theory confronts is the mysterious particle known as the tachyon. This enigmatic particle poses a significant mathematical problem within the theory. The tachyon's mass, according to the theory's calculations, emerges as an imaginary number, the square root of a negative value. In the realm of physics, imaginary masses are not only unfamiliar, but can also result in inconsistent and nonsensical predictions. To create a theory that adheres to the laws of physics as we know them, physicists must grapple with this issue and develop a resolution. The tachyon's existence raises questions about the stability and coherence of string theory. Understanding and eliminating this mathematical oddity is a crucial step toward creating a comprehensive and reliable theory that aligns with observed reality. Perhaps one of the most confounding challenges of string theory is the discrepancy between the dimensions it requires and the dimensions we observe in our universe. Our reality is composed of 4 dimensions, 3 spatial dimensions, and 1 dimension of time. String theory, however, appears to necessitate a universe with a whopping 26 dimensions to accurately accommodate its equations. This drastic mismatch raises the puzzling question of why our universe, with its 4 dimensions, should fit within a framework that demands so many more. To address these challenges, further development of the theory is essential. To account for fermions, scientists propose adding something called spinors to the strings. These spinors are mathematical tools that already help describe fermions in the standard model. By introducing spinors to strings, we can potentially overcome the challenge of predicting fermions and address the tachyon issue. This enhanced version is named superstring theory. Interestingly, by adding spinors, the theory gains a new symmetry between fermions and bosons. This symmetry, known as supersymmetry, suggests an equal balance between the 2 categories, implying that for every boson, there should be a corresponding fermion. However, the question of dimensions still persists. Before accounting for supersymmetry, mathematics indicated a universe with 26 dimensions. With the inclusion of supersymmetry, superstring theory instead suggests a universe with 10 dimensions. This discrepancy remains a puzzle, as it doesn't match up with our 4-dimensional reality. Neil deGrasse Tyson's skepticism about string theory seems to stem from his experience with its progress and potential. He initially supported string theory when it emerged in the early 1980s as a theory of everything that could bridge the gap between Einstein's theories of relativity and quantum mechanics. Tyson recognized its potential to explain the universe's fundamental properties, such as the moment of the Big Bang and the behavior of matter at both the macro and micro scales. However, over time, Tyson's enthusiasm waned as progress in string theory was slow and unfulfilled promises of breakthroughs persisted. He highlights that since 1985, string theory was a couple of years away from completion, a statement that became less convincing as the years stretched to more than 2 decades. Tyson acknowledges that string theorists don't attribute their difficulties to human inadequacy, but he humorously suggests that perhaps humanity, as a species, is too challenged to grasp the complexity of the theory. Despite his skepticism, Tyson recognizes that string theory researchers are essential because they are the only game in town. He acknowledges their efforts and the fact that they're inexpensive to fund. However, his enthusiasm diminishes as he comes to realize the theory's difficulty and the lack of progress compared to the expectations set in the early stages. Now let's discuss Neil deGrasse Tyson's views on dark matter.
We look in the universe and we see the effects of gravity, and let's say, let's add up all the stars and galaxies and planets and comets and black holes, everything we know about, to account for this gravity that we see. And when you add in the dark matter, this extra gravity, it turns the universe into the universe that we see. That's why we know the dark matter is real. We don't know what it is, but we know it's there because we can't make the universe as we see it unless we put this extra gravity into our simulations to match the gravity that we see. Particle physicists are convinced that it might be an exotic particle that doesn't interact with us, doesn't interact with our light, with our telescopes, but that it has gravity. So these particles are doing their own thing, invisible to us, but otherwise attracting our matter into nucleating us among them.
Neil deGrasse Tyson brings a fresh perspective to the existence of dark matter, challenging the notion that it is indeed a form of matter. His insights shed light on a fundamental misunderstanding that has the potential to redirect scientific focus. Dark matter, he contends, may not deserve the label it has been given, as it might not be a form of matter at all. Tyson raises a critical point. Our comprehension of dark matter remains severely limited. Unlike other entities in the universe, dark matter cannot be directly observed. Its existence is inferred through its impact on other objects. He humorously proposes renaming it Fred, a name that bears no implied meaning, an apt reflection of our current level of knowledge. By suggesting an alternative moniker, he seeks to shift the narrative away from the preconceived notion of matter. As an alternative, Tyson introduces the concept of dark gravity, a term that offers both accuracy and intrigue. He presents a staggering statistic. When all elements of the universe, such as stars, moons, gas clouds, and black holes, are taken into account, a perplexing reality emerges. Approximately 85% of the universe's gravity remains unexplained, a phenomenon known as dark matter. The conventional narrative may fixate on its existence, but Tyson argues that the true fascination lies in understanding why it lacks interactions with the familiar matter we know. What Tyson offers is not a negation of dark matter's significance, but rather an invitation to reimagine its nature. His alternative terminology encourages scientists and enthusiasts alike to approach the subject with a fresh perspective, unburdened by the presupposition of it being a conventional form of matter. By rebranding dark matter as dark gravity, he advocates for a shift in focus, one that embraces the mystery, seeks understanding, and encourages investigation.
It may be that the dark matter is not matter at all. It's the gravity from ordinary matter from a nearby other universe in the multiverse, whose gravitational influence we feel. And here we are, saying, ooh, we have a mysterious gravity, call it dark matter. Really, it's just ordinary matter doing its thing in an adjacent universe. We don't have data for this, but we have good theoretical and philosophical reasons to think that a multiverse exists.
Now let's delve into Neil deGrasse Tyson's thoughts on the multiverse theory. But first, we need to know what the multiverse theory is. The multiverse theory is a speculative concept in theoretical physics and cosmology that suggests the existence of multiple universes or parallel universes beyond our observable universe. These universes could have different physical laws, constants, and properties, making them fundamentally distinct from our own universe. There are several variations of the multiverse theory, but one of the most well-known is the many worlds interpretation of quantum mechanics. According to this interpretation, every quantum event that has multiple possible outcomes creates a branching of the universe. In each branch, a different outcome occurs, leading to the existence of countless parallel universes. Another version of the multiverse theory arises from cosmic inflation theory, which suggests that the universe expanded rapidly in its early stages. In this scenario, different regions of space would stop inflating at different times, creating separate bubble universes within their physical properties. Neil deGrasse Tyson, like many other physicists, acknowledges the existence of the multiverse theory as a possible explanation for certain phenomena in cosmology and quantum mechanics. He doesn't explicitly claim that the multiverse definitively exists, but rather he considers it a plausible and intriguing hypothesis that's worth exploring. Tyson often emphasizes that our understanding of the universe is limited by the tools and methods available to us. He recognizes that the concept of a multiverse might sound exotic and even unbelievable, much like the initial suggestions that the Earth orbits the Sun, or that our galaxy is just one of many in the universe. He draws parallels between these historical breakthroughs and the possibility of a multiverse. In his perspective, Tyson suggests that even if the multiverse seems far-fetched, it's not necessarily more crazy than previous ideas that have become widely accepted in the scientific community.
The laws of physics as we experience them are set in the very earliest stages of the universe. And quantum fluctuations in everything would be responsible for another universe having slightly different laws of physics than ours. Because the quantum fluctuations will take it in a slightly different law of physics direction than our universe. And this would just keep going. With the multiverse, where there could be pockets of the universe that are expanding with no knowledge of any other pockets of the universe. These are essentially independent universes from one another, and never the twain will meet. Imagine you're a ship at sea and you look to the horizon, and that's your whole universe there, to the horizon. There's another ship that has its own horizon, and these ships don't even see each other. You'll only see each other if somehow your two horizons can overlap. And we don't know how to do that in our universe because they're non-causal. You'd have to find some way to tunnel from one universe to the other in order to access that, but that could be very dangerous. Because if the laws of physics are different than the ones you evolved on, then you could just dissolve into a pile of goo because the charge on the electron is different and all of your biochemistry would change.
The concept of a multiverse is intriguing, yet it's important to clarify that there is currently no direct empirical evidence that definitively proves the existence of a multiverse. While there isn't conclusive proof, there are theoretical arguments and observations that some proponents of the multiverse theory find compelling. Let's discuss a few concepts and arguments that have been put forth in discussions about the potential existence of a multiverse. The Many Worlds Interpretation, or MWI, is a provocative theory within quantum mechanics that suggests every possible outcome of a quantum event actually occurs, creating multiple branches or parallel universes. This interpretation seeks to address the puzzling behavior of particles at the quantum level, such as particles seemingly existing in multiple states simultaneously until observed. In the MWI, the universe continuously splits into separate branches whenever a quantum event occurs. For example, in the famous Schrödinger's cat thought experiment, where a cat could be both alive and dead simultaneously, the MWI proposes that each possible outcome happens in different branches of the universe. Critics of this interpretation argue that it introduces an excessive number of parallel universes and raises questions about the meaning of reality. Proponents, however, contend that the MWI provides a coherent explanation for the quantum realm's inherent uncertainty. Cosmic inflation theory posits that the universe underwent a rapid expansion in its early stages. Some versions of this theory suggest that different regions of space stopped inflating at different times, resulting in bubble universes with distinct properties. These bubbles could exist within a larger, inflating space, forming a multiverse. Imagine inflating a balloon with dots on its surface. As the balloon inflates, the distance between these dots increases, much like how different regions of space can stop inflating at varying times. Each bubble universe within the larger space could have its own set of physical constants and laws of physics. However, confirming the existence of these bubbles and their properties remains a significant challenge. The anthropic principle addresses the peculiar fact that our universe's physical constants and properties appear to be finely tuned to allow for the emergence of life. If any of these constants were even slightly different, it's possible that life as we know it would not exist. The fine-tuning of the universe raises questions about why these constants have the values they do. Proponents of the multiverse theory suggest that the existence of a vast array of universes with varying constants and properties increases the likelihood that at least one universe would have the conditions necessary for life. This version of the multiverse is often referred to as the multiverse of fine-tuning. Critics of the anthropic multiverse argue that it might be a tautological explanation, as it doesn't necessarily provide insight into why the constants have specific values in the first place. Additionally, the anthropic principle raises philosophical questions about the role of observers and the nature of reality. The cosmic microwave background, or CMB radiation, is the afterglow of the Big Bang and provides a snapshot of the universe when it was just 380,000 years old. While the CMB has been a crucial source of information about the early universe, anomalies and patterns in its distribution have sparked discussions about the multiverse. Some proponents of the multiverse theory argue that certain features of the CMB could be evidence of interactions between our universe and other universes. These interactions might have left imprints in the CMB, resulting in patterns that cannot be explained solely by our universe's evolution. Critics, on the other hand, caution against jumping to conclusions. They point out that anomalies in the CMB could also have other explanations, such as cosmic variance or systematic errors in measurements. Furthermore, the current state of our observational technology and our understanding of the universe's early moments limit our ability to confidently attribute CMB patterns to interactions with other universes. Thank you so much for watching this video. If you found it informative, don't forget to give it a thumbs up. And if you have any questions or suggestions for future videos, please feel free to leave them in the comment section below.